Welcome. Now we will look at something called partial molar properties, which are essential whenever you consider any mixtures or solutions. Let us start with the Lewis and Randall rule itself. From the Lewis and Randall rule, which is valid for an ideal gas equation, we can expect that in general the property of a component I in a solution may not be the same as the pure state property at the same pressure, at the same temperature and the same total pressure. Therefore, we cannot use a weighted average. What we did in the case of the ideal gas solution is that we used a weighted average. Fi hat equals yi times Fi, yi was the weighting factor there. Here if it is a non-ideal solution, we cannot do that. We can do that only for an ideal gas solution. Therefore, we use something called partial molar properties. To know what partial molar properties are, let us take M superscript T, Mt, to be any extensive total thermodynamic property. Okay, we have seen this already. For example, it could be Ut, which stands for the total internal energy, St total entropy, Ht total enthalpy, At total Helmholtz free energy, Gt total Gibbs free energy, or Vt total volume. If this is the case, then the partial molar property, which I am going to represent as MIT with a hash over it. MIT is the total property, is the property of the component I in the total solution. With a hat, it becomes a partial molar property. It is defined as equal to dou Ni of Mt at constant temperature, pressure and all other mole fractions remaining the same. Again, MIT hash, the partial molar property, is defined as dou Ni of Mt taken at constant temperature, pressure and all other mole fractions remaining the same. We will call this equation 411. This will become clearer as we go along. And as we had said earlier, the partial molar property may not be the same as the pure state property, the same temperature and total pressure. That is a reason for defining something different as the partial molar property. It is the property that it seems to exhibit when it is present in solution. In other words, it is some sort of a hypothetical measure. Why are we using this measure? It gives us an easy means of calculating the total property or estimating the total property. The total extensive property in turn can be computed from the partial molar properties as Mt is nothing but sum over mole fraction Ni times the corresponding partial molar property MIT hat. So, this is a simplistic formulation. To be able to do this, we go in for some sort of a conceptual partial molar property. What I would like you to do is take a few minutes and write down this expression for each one of these partial molar properties that we have seen so far. There are about 6 here. Please write them down for each of those properties, this expression. Go ahead and I will present them in the next 5 minutes or so, after 5 minutes. Go ahead please. Okay, you would have found it reasonably simple to write this down. Vt total volume is nothing but summation of Ni times partial molar volumes ut is nothing but summation over Ni times partial molar internal energies of each component. St is nothing but summation over Ni Si t hat. Ht is nothing but summation over Ni Hi t hat, the partial molar enthalpies times the mole fraction of each enthalpy summed over all i's gives you the total enthalpy. At is nothing but sum over Ni At hat, and Gt is nothing but sum over Ni Git hat. It is nice to have this here. You can refer to this from time to time. Equation 4.13. The dashes are somehow not visible in some cases. Please make sure that these dashes are present in all your quantities. Now, we have already seen this, that the partial molar property is defined as dou Ni of Mt at constant T, P and J. Does this remind you of something that we have seen earlier in the earlier module? Think about it. If any extensive property can be written as a function of T, P and Ni, then the total differential can be written as, this is again an exact differential. Therefore, you could write the total differential dmt, or this is a state function. Therefore, you could write the total differential as dmt equals dou t mt at constant p ni dt plus dou p mt at constant t ni dp plus summation over dou Ni of Mt at constant T, P and J. Here we had taken Mt as a function of T, P and Ni, or what is this? This is nothing but the partial molar property. Therefore, dou Mt dou T at constant P Ni dt, dou Mt dou P at constant T Ni dP plus the partial molar property, the sum of the partial molar properties times the dni for each species. That is the total differential here. We will call this equation 414. The total differential from equation 412, which is this, Mt equals summation of Ni times the partial molar property of I. You take the product of each and sum them over, that will be equal to the total value, the total extensive property value. This is equation 412. If we differentiate this, we get the total differential dmt equals summation of Ni times the partial molar property of I plus the partial molar property times dni. This essentially comes from using the chain rule here. Sum over each one of these terms, you could do the chain rule for each of these terms and then separate the terms, group them appropriately to sum them over Ni dmit plus summation of mit dash dni, essentially chain rule application. So, we have the total differential from this expression 414 as this on the right hand side, and the total differential here. What I would like you to do is equate the right hand sides of 414 and this particular expression, which is equation 415, and tell me what you get. See whether you get something interesting. Take the next 10 minutes to do that. Go ahead, please. Okay. I had asked you to equate dou T of mt at constant P n I dt, dou mt dou P at constant T n I dP plus summation of mit hat dni with summation of ni times the partial molar of I plus the summation of the partial molar property times dni. If you do this, you can see that one of these terms is going to cancel out, then you should have gotten dmt dt at constant P n I dt, this is the same term as earlier, plus dmt dp at constant T n I dp, again same term as earlier, and what does not cancel and gets transposed to give you minus summation of ni dmit as this term. So, this term essentially gets cancelled with the same term as on the other on the right hand side of equation 414. Therefore, dou mt dou T at constant P n I dt, dou mt dou P at constant T n I dP plus summation of ni dmit, this equals 0. Are you able to see some nice thing here? We will call this equation 416. So, this is if you write it in terms of g, you will see that g is a function of T p and mu. Therefore, you can probably make the connection with something that we have already done earlier. Now, at constant temperature and pressure, this equation 416 that we saw, this we are writing for all partial molar properties. So, if we instead of concentrating on G alone, which we had done somewhat earlier in the earlier module, we will do it for any total property. If we do that at constant temperature and pressure, these two terms are going to get to 0 because dt is 0, dp is 0. Therefore, what remains is summation of ni dmit hash equals 0. We will call this equation 417. If we divide summation of ni dmit hash equals 0 by the total number of moles, each term in the sum gets divided by n, and therefore, each of these ni's can be replaced by the mole fraction. That is the definition of mole fraction, ni by n is the mole fraction. Therefore, when you divide it by the total number of moles, you get sum over xi dmit hash equals 0. This is equation 418. This is quite a powerful equation, as we will see later. I think we are almost out of time for this particular class lecture. Let us stop here and continue from here in the next class.